So hi, I'm John. As you will have heard, I am a particle physicist. The title of my talk kind of changed, actually, when I didn't like it like 2 days ago. So it was inference-aware optimisation, that bit's fine, and likelihood-free inference with normalising flows. It's not quite right, actually, likelihood-free inference, so I'll change it to simulation-based inference. I thought it'd be nice if I just kind of introduce how I've got to this point. So I did a physics degree at the University of Manchester from 2013 and graduated in 2017, and then since then I've been at Imperial, first doing my PhD and then a research associate position, so a postdoc, and then came to this AI and Science Fellowship at the beginning of 2023, and basically these second, third, and fourth blocks have all been where I've been working at the CMS experiment, which is an experiment at the Large Hadron Collider at CERN in Switzerland. Okay, so on to what I'll talk about today. So statistical inference is this key aspect of any kind of experiment, scientific analysis. It allows us to make some understanding of the data. For many fields, unfortunately, we're no longer in this regime where we can just write down an analytic likelihood for inference. So the systems that we're studying are becoming increasingly complicated with many unobserved latent variables. The example I show here is, for example, is disease modelling in the population. So, say we have model parameters that we want to infer, like R0 or mortality rate, and the data that we get are things like positive cases, number of hospitalizations, deaths. How can we, from this data, infer the underlying model parameters when, in between all of this, we have many unobserved latent variables? So things like level of social mixing, how many people are actually wearing masks, level of caution, etc. And the way we do this, a method for doing this, is simulation-based inference. So it's a way that we can basically estimate these intractable likelihood functions. This is basically the notation that I'm going to use throughout the talk. So our likelihood function, which basically says the probability that we observe some data x given some model parameters theta, and where they're the parameters that we're trying to infer, is an integral over all possible trajectories through latent feature space. Okay? So z are these latent variables. We don't particularly care about them. We need to integrate over all possible trajectories to solve this likelihood function. And the way we do this is by using simulation. So we have high fidelity stochastic simulations to generate some synthetic data, and then we can use this synthetic data for inference, which we basically compare the synthetic data to observed data to infer the model parameters. There's two traditional approaches to inference. One is approximate Bayesian computing. I won't cover that in the talk today. What I'll be focusing on is the second. So using the simulated data to estimate the underlying probability density. And just to say, SBI is not particular. It's not special for particle physics. It's used basically across the board at all these different kind of length scales, like protein folding, neuroscience, climate science, etc. But I'll be focusing on SBI in particle physics. At the LHC, we collide protons together at 40 million times a second, and from these proton collisions, we get data. So our collision data basically constitutes many independent, identically distributed data points, observations. So then we can say our likelihood, so our probability of data given some model parameters is basically the product over the probability for each data. Our data is very high dimensional. We have many final state particles coming out of these collisions. And from each of these, we measure things like their energy, momenta, identification. So we're dealing with very high dimensional data. And this really requires, to make sense of this data, stochastic simulation with millions of latent variables. So in terms of SBI, there's been a bit of a revolution over, I'd say, the last half a decade. And three forces have led to this rapid expansion of simulation-based inference as a field. The first being advances in ML. The second is active learning. So as you're performing the inference, you locate which region of parameter space looks sensible, and then you guide the simulator to generate data from those particular model parameters. The third is an interesting idea of actually within the code itself, being able to pick out the values of the latent variables that produced a particular value of the synthetic data, and then you can kind of condition on these trajectories. So the second and third one here, I'm not actually going to cover today. I just wanted to highlight that these are interesting things that have led to the advancement of SPI. What I'll be talking about is new approaches in ML revolved around simulation-based inference. So just to give an overview, I'll start by just giving a very dummy few slides on an introduction to collider physics, and then talk about how we do statistical inference at the LHC. And then following this is kind of like the meat or the more interesting parts of the talk. Firstly, talk about inference-aware optimisation, so a method where we tune the loss function of our neural network towards a specific inference task. There's a tutorial for this as well. Hopefully we'll have time to go through it and also discuss the last point, but I'll play that by ear, and if not, then I'll just give you a link to the tutorials for you guys to go through in your own time if you're interested. And then the final part is looking at a specific type of network architecture called normalising flows and how we can use those for SPI. And yeah, just to make absolutely clear, if you've got any questions throughout, just speak up. Please feel free to interrupt. Okay, so on to an introduction to collider physics. What we're trying to do in fundamental physics is basically to understand the evolution of the universe from the Big Bang to the stars and galaxies that we see today. So we can do this in two ways. One is to approach the diagram from the right-hand side, so looking at the larger scale structures in the universe with things like the James Webb Telescope. But we can also approach the diagram from the left-hand side, so probe these smallest scale structures that we have in the universe at particle observatories like the Large Hadron Collider, where we're really trying to recreate these high energy, high density conditions that we had at the early universe. What do we know? So we have this really successful theory which describes particle physics at the energy that we can probe it at the minute. That's called the standard model of particle physics, and it basically describes the fundamental building blocks of nature. So we can break this down on the diagram that you see on the left. It's kind of like a periodic table, if you like, in a way, but now about the fundamental building blocks of the universe. So we have the fermions, which are the matter particles, and these themselves are split up into the quarks and the leptons. Quarks come in three pairs of two flavours. So we have up, down, charm, strange, and then the heaviest are the top and the bottom quarks. Then we have leptons, so the most famous being the electron, which is a fundamental particle. This is a charged lepton, you've got electron, muon, and taus, and then we also have the neutrinos, which are very light neutral particles. So they're the matter particles. As well as this, we have the bosons. The bosons are basically the force mediators. So they describe how the fermions interact with each other. For this, you have the gluon, the photon, and the W and Z bosons, and these are responsible for the electromagnetic, strong nuclear, and weak nuclear forces. And then the final piece of the puzzle is the Higgs boson. Okay, so this is what provides all of the particles that have mass in the standard model, their mass. What you see on the right-hand side is like the quite explicit mathematical formula that we have for this particular theory. Right, so this is known as the standard model Lagrangian. Haven't put it in its most compact form. I just want to give you an idea of the complexity that's involved with this particular mathematical function. And it's the parameters of this standard model Lagrangian that we're trying to measure. So these are our theta parameters, things like the masses of the particles and their interactions between each other, the strength of the interaction. Okay, so that's all well and good. Unfortunately, it's incomplete. So this theory here is a perfect description in terms of what we see at the LHC for these forces, but we know from other physical evidence that it's not complete. So straight off the bat is gravity. There's no quantum theory of gravity in the standard model. On top of this, from like other cosmological observations, we know things like dark matter and dark energy have to exist, but they're not described by the standard model of particle physics, nor can it explain the matter-antimatter asymmetry that we see in our universe. So it does have its shortcomings. The upside of this is that there must be some new physics to discover, so it's keeping people like me and Mikhail in a job. And this is what we're trying to do at the LHC, so discover new fundamental physics. So how do we do that? There's two ways, really. One is by directly observing new particles in the data. So basically like bumps in the data, which would represent new particles. The second approach is kind of like an indirect observation. So we precisely measure the particles that we know about and look for deviations in their interactions, like their coupling strength, etc., from what the theory tells us. And that would be a sign of new fundamental physics. Now, both of these approaches require, one, high energy. So, Einstein's equation, E equals mc squared. To be able to create these interesting particles with a high mass, we need to collide particles together with a lot of energy. And also high intensity. So we need a lot of data to do that. And the way we get a high energy, high intensity machine is from these particle colliders. So basically, we have two opposing beams. We accelerate the particles in these beams to very high kinetic energy, and then collide them and basically measure what stuff comes out of these collisions. And if we do these collisions with sufficiently high energy, then we can produce some of the rarer particles in the standard model. So things like the top quark, the W and Z bosons, and the Higgs boson. So what's the status now? So we have this collider called the Large Hadron Collider, the LHC. This is the most powerful collider we've ever built. So it's a 27-kilometre long ring of superconducting magnets, which sits around 100 metres underground the French-Swiss border near Geneva. So it's absolutely huge, 27 kilometres long. And then within this ring, we accelerate protons to basically the speed of light, and just shy of the speed of light, and collide them together. And these collisions happen 40 million times a second at 4 points along the ring. So that's the CMS experiment, the ALICE experiment, the LHCb experiment, and the ATLAS experiment. Okay, so at these interaction points, at these experiments, the collision fragments are basically photographed with these massive imaging detectors. What I want you to take from this slide is that proton collisions are extremely messy. So we need to be able to infer what's going on in the centre here from all of the stuff that comes out. And the only way we can do that is by having these state-of-the-art detector technologies. Yes?
How do the imaging detectors work? Do they look at photons or?
Imaging, yeah, so imaging should be in quotations as well as photograph. We have loads of different types of detector technology. There is actually kind of like an imaging thing. There's pixel detectors right at the centre point. But then apart from that, like as you grow out from that, you start to have like calorimeters, I don't know if you, and like scintillators, all that kind of stuff. So imaging take with a massive grain, like pinch of salt. Yeah.
They used to take photos.
They used to take photos, yeah, back in the like 70s and things. Bubble changes. Well, even before that with like the positron discovery. But we've gone a long way since then, and that's like where we're at now. So this is the CMS experiment. That's the experiment that both myself and Mikhail work on. And this is one of two general purpose detectors at the LHC. And again, I put this in quotations. You can kind of think of this as like a giant camera operating at 40 million frames per second. It's not a camera. It has many different types of detector technology. But that's the basic idea. So on the left is my attempt at making like a CMS top trump card. The length, again, what I want to say is this thing is absolutely massive, right? The length is 28 meters. Its diameter is 15 meters. And it actually weighs more than the Eiffel Tower. So it's a huge machine. I realised the picture that I chose, the only person to give you scale is this head down here. And it doesn't give you a good idea of the scale. But yeah, hopefully from these stats that you can see, this is pretty huge. So the central feature is this grey ring here. So this is the superconducting solenoid magnet. which provides a 3.8 Tesla magnetic field, so a very strong magnetic field. And the reason that exists is so that when we create charged particles from these proton-proton collisions, the charged particles are basically bent in this solenoidal magnetic field. And from the amount that they bend, we can infer like their momentum. Okay? And then inside of the solenoid and outside, we have these kind of like layers of different types of detector technology. So these what we call subdetectors. And because it has this layer structure, we say it's kind of like a cylindrical onion. In terms of the readout channels, there's a ridiculous amount, right? Order 100 million readout channels in the CMS detector alone.
So what is a readout channel?
Just like where we'll collect data from one part of the detector. So particle goes through, it creates an electronic signal, and we read out that electronic signal. Yeah, and for that across the whole detector, we have order 100 million of these readout channels. So you can start to think already we're dealing with like very high data rates. If we're colliding protons together at 40 million times a second, and you have order 100 million readout channels, this is a ginormous amount of data. And the other thing to say as well, this all has to operate in a very extreme radiation environment. We're basically battering this machine over decades with really high particle flux, and the detector needs to be able to withstand this. So what does a collision event look like? So the first thing to say is that interesting physics that we're trying to measure is unstable. So things like the Higgs top quark, the W and Z bosons, they basically decay instantaneously. So they decay before reaching the detector. So we produce them at this interaction point here, and then they decay straight away. And we can only infer its presence from what it decays into. And these diagrams on the left, these are what we call Feynman diagrams. So you read them basically from left to right along the time axis. You have your quarks from the colliding protons coming together that fuse and create some high mass particle, like the Z boson or a top quark pair. These decay instantly, and then it's this final state particles which we measure in the detector. And it has this particular structure so that we can measure all of the different types of particles that come out. So things like muons will go all the way through the detector and leave a signal in the muon chambers. Everything else will be stopped, or tends to be stopped before that. Things like hadrons will shower in the hadronic calorimeter. Electrons and photons will shower in this thing called the electromagnetic calorimeter. And then we can infer the presence of charged particles from their tracks in this inner tracker. Okay? So it's the combination of all these things together which allows us to understand what's going on in a collision event, and then from that infer what happened right at the interaction point. So this is what an event looks like, a typical reconstruction of events. We saw this on the intro slide. This is the colorized version. So this is a Higgs boson decaying into 2 photons. So as I said, the Higgs is unstable, it decays instantaneously. We don't see that in the data. What we see are the towers of energy which reach into the electromagnetic calorimeter, and these are the 2 photons. So what we can do is basically sum up the momenta of these photons, and from conservation momentum, we'll be able to infer the mass of the particle that's produced them. And that's why we find a bump in the data at the Higgs boson.
But we do definitely know that it's coming from a Higgs boson?
No. I should really have put a plot that shows the mass spectrum here. I'll come on to it. Basically, we deal with, in very basic terms, signal and background. And we're often dealt with much larger backgrounds than we are signals. So we need to basically come up with a way to identify Higgs boson signal, whereas background is just any other process that can produce 2 photons. Yeah, and that's basically the main part of the talk. So we'll come on to that. All right, so yeah, I kind of already said this. This coupling of the 40 million proton collisions that we make a second with the order 100 million readout channels means that we're really dealing with extremely large data sets. So this is my attempt to kind of like give the data volume some understanding. So it's around 500 terabytes of data which flow through the detector. And what that equates to is around, well, at least 1,000 times the Lord of the Rings trilogy in 4K per second. So there's a huge amount of data. We can't, of course, record all that data to tape. We have to throw away quite a lot of that data. And we do that with a real-time processing and filtering of the collisions, which is something that we call the trigger. But even after this hardware trigger, we have around tens of petabytes per year saved offline for further analysis. So it's huge amounts of data. On top of that, it's not just like boring data, it's extremely diverse, right? We have many sub-detectors, all with different geometries and readout, providing particle measurements in spatial and temporal dimensions. So it's a really diverse data set. It's well understood. There's small uncertainty in the data. We know where these particles go to a high precision. And significant time is spent in the experiment making the data set well structured, so easy to play with. So it's these four things that really make the LHC experiments an ideal playground for AI and machine learning. So it's used basically across the board nowadays. Things like the trigger, which I spoke about, accelerating our computing, reconstructing the collision events, and like classifying what happened in the events and optimizing the searches for interesting physics, right down to the statistical analysis. And it's these two final points which I'll kind of speak about today. Okay, so back to this image. Our proton-proton collision data is a high-dimensional mess, right? So we have many, many final state particles which come out from these collisions. We record their energy and momenta. How can we make any sense of this data? How can we infer these underlying parameters of our mathematical model from this? And the only real way that we can do that is by simulation. So we need to simulate what is happening in the detector, right from the mathematical theory, so our standard model Lagrangian. From this, we can generate basically hard scattering interactions. So this is the kind of process which is happening at a high energy. This is where your Higgs bosons and top quarks and W bosons exist at a very high energy. But that's not what we see in the detector, right? We need to then run this down for a process known as parton showering and hadronization to lower energy particles, which is what we see in the detector.
Sorry.
Yeah.
Fundamental question.
Yes.
Do you know how many latent variables to model?
Yeah, you don't know a priori, right? It's over time that you develop your simulation to
So you incrementally.
Yeah, and for the detector part, you really build a geometric model on a computer of all of the different parts of the detector with each of the different readout channels. Now, each of those can introduce a latent variable. So straight away there, you've got millions, order 100 million latent variables, right? Here you have many different latent variables which are describing the non-perturbative quantum effect of running this hard scattering process down.
So there's no notion of covariance between the latent variables?
Not at this stage, no. It's almost like a stochastic simulation, yeah. So it's very complicated is what I wanted to get across on this slide, right? Not only then have you got this top bit's being what happens in the theory, you then need to understand how those collision events interact with the detector medium. And then even then, you need to simulate the electronic signals and how we reconstruct the electronic signals. And eventually that's what we get, the data. So it's this extremely sophisticated chain, and we do simulate the whole chain. So right from the mathematical theory all the way through to the observed data. And then we can compare this synthetic data to what we see at the LHC to go all the way back through the chain and infer something about these model parameters. Okay? So going back to this likelihood definition, so this is the likelihood of some data given some model parameters. Again, it's this integral over the many different latent features that we've introduced at each part of this Monte Carlo simulation chain. So all in all, we're saying that the particle physics likelihood is highly intractable. We can't simply take the events that we see at the LHC and the model parameters and compute the likelihood. And it's not even just this, the fact that we're introducing many latent variables. The actual processes that underpin this are intrinsically intractable. Quantum mechanics is non-deterministic. So to basically evaluate this integral, we use high-fidelity Monte Carlo simulation, which does the full chain, simulate each part of the chain in sequence, and from this we obtain this sample of truth labelled synthetic data, which is processed in the same way as the real data, and then we can compare our real data to this labelled data for inference. Was that all clear? Hope so. Okay, so this is just a slide to show that despite being extremely complicated, this whole chain of what we're trying to simulate, we do a pretty good job. So this is a mass spectrum for Z to EE events. So Z bosons are going into 2 electrons. And we calculate the mass of these 2 electrons, and we expect to get a peak at the Z boson mass. The black points is what we collect at the LHC. So you get this peak structure at the Z boson mass, and then the purple histogram is what we simulate. And you can see in the ratio plot below, which in each bin of this histogram is just your data over Monte Carlo, that we're doing a very good job at simulating what we see in the detector.
So
The ratio, yeah.
basically what happens is you choose a bunch of thetas, do the simulation, compare to the real data. If they look similar, then you keep the thetas.
That'd be more on the ABC side. I'll go into how we do this statistical inference. It's more like a density estimation approach. So for a given set of thetas, like using the Monte Carlo to approximate what fraction of data, events would land in these bins of the distribution. Okay? So go all the way through the chain and you estimate what the probability density would be.
So you have a distribution over the possible probability densities, and then using the Monte Carlo to kind of pick the right distribution from that.
Our Monte Carlo is for, an example would be, let's pick this coupling here. Right, if we increase this coupling, then you'd expect, which is that'd be like a theta parameter, the coupling between the Z boson and the quarks. So this is your quark interaction with the Z boson. If you increase this coupling, then you'd see more Monte Carlo. Sorry, that's the wrong thing to say. If you increase this coupling, then you'd see more data at the LHC, right? So the back would increase. And then we can use our Monte Carlo for a fixed value of theta to say, okay, this is the value we expect for that, but okay, right, it doesn't align with the data. How can we tune that theta parameter so that our Monte Carlo aligns with the data? And the point where it fits best is what we say, okay, that's our best fit point for that parameter of interest. That's I will come on to that in a bit more detail in a few slides when we go through how we actually do this statistical inference in practice. Okay?
So here you've given us the result of the simulation without.
Yes. Yeah. This simulation has gone all the way through this chain, right? So we have interaction, mathematical description of our interaction. We simulate this hard scatter, which is like what you see here, and then we take these electrons, we run them down. Oh, wrong way. Sorry. We run the event down, and then we simulate how these electrons interact with the detector medium, and then how we reconstruct that, and then process the data in the exact same way as the LHC data, and that's what we get. So we get something that aligns well with the data that we've collected at CMS. Okay? Yeah?
What's the error of your data?
The error?
Yeah.
Yeah, so that's a really important part of this whole talk, which I will come on to. Okay. So the error in the data is statistical, right?
Okay.
So it's just like for a given bin of the histogram, it's kind of like a Poisson count in that bin. So given some expectation, how many events would you see in this bin? So that's just a purely Poisson statistical error on the data. For the simulation, which I'll come on to talk about, you have the statistical component as well. You can only simulate so many events, but also you have to introduce like a systematic uncertainty. So these are like nuisance parameters, which would model how the detector, how particles interact with the detector and things like that. Yeah, I'll come on to that because that's basically what the whole point of the talk is. All right. So, yeah. this, what I want to just do is boil down what I mean by the data here, right? So these are the observables, things like the reconstructed energies, momenta, and angles of the final state particles that we get in these collisions. And we want to infer something about these fundamental physics parameters of interest. So, for example, how strong is the interaction between the Higgs boson and the top quark? Now, this data is still of a high dimension, right? So all of these final state particles having their energy, momenta, and angles, which means that if we want to accurately estimate the underlying density, so your probability of this data given some model parameters, we need a lot of Monte Carlo simulation. And given how complicated the whole chain is, as I've shown, it's a computationally expensive task to simulate Monte Carlo for particle physics experiments. So when the data is of such high dimension, it's basically infeasible to try and accurately estimate the probability density in the full high dimensional space of the observables. So what we do is, for SBI, we typically construct lower dimensional summary statistics. Okay, so we take high dimensional data and in some way, which I'll go on to describe in a few slides, take this down to a much lower dimension, typically by histogramming the data in a particular variable, and then we can use this lower dimensional variable to do the inference. So our Monte Carlo simulation can estimate the density in these lower dimensions much more accurately, and then we can compare that to the data to infer something about the physics. Now, this act of reducing the dimensionality of the data invariably discards some information, right? So we're going to lose some information about the model parameters from our data by this dimensionality reduction. The task which I'm putting forward is to retain as much information about the model parameters in the summary statistic as possible. Okay? So that's what we're trying to do. We're trying to come up with a way to define a summary statistic which maximizes the information about the parameters that we're trying to measure. Okay, aside. Higgs boson physics. So this is what I work on. The first thing to say is that our universe is strange. So as far as we know, all of these fundamental particles, they're point-like. So they don't have any like physical size, which means that without some, apologies Mikhail for writing the word magic here, without some additional mechanism into the standard model, it only works for massless particles. And the universe full of massless particles, so particles without mass, would be extremely boring because everything would just move at the speed of light and you wouldn't be able to form any structure. So no chemistry, no biology, no life or anything, right? What was theorized back in the 1960s is this Brout-Englert-Higgs mechanism, which basically introduces this spontaneous symmetry breaking event just after the Big Bang, where the Higgs field rolls down its potential well. So it starts off at a value of 0, and it rolls down its potential well to take a non-zero expectation value in the vacuum. Okay? So it's a mathematical field that's non-zero everywhere in space. This non-zero is crucial because now as particles move through space, they interact with the Higgs field. Right? And it's this interaction which creates basically like an inertia. It's this like slowing down. So as particles move through the Higgs field, they interact with it, they're slowed down. That's the analogy I'm going through with honey here. If you were to walk through honey, you'd feel some inertia, and that would make you feel very heavy. Right? So as particles move through the Higgs field, they're slowed down by interactions with the field. And this is the inertia which we actually identify as mass. Okay, so that's what mass is. All right, so we have the theory. How do we prove this experimentally? Now, if we collide particles hard enough, then they can cause ripples in this Higgs field, quantum excitations of the Higgs field. And it's these quantum excitations which we identify as Higgs bosons. So from the 60s, we knew this kind of thing had to exist, but we didn't have any experimental data to prove it. And the reason is because we need extremely high energy and intensity to do that. So Higgs boson production is extremely rare.
So ripples
yes.
in the Higgs field are equivalent of the honey that is the resistance, is what you're saying?
Yes. Yeah. And is that this inertia Which, yeah. So Higgs boson production, even at the LHC, is extremely rare. So only around 1 in 10 billion proton-proton collisions produces a Higgs boson. So it requires sophisticated analysis techniques, for example, machine learning, to find this small signal over a much more dominant background. So this goes back to what we were speaking about before, right? So with like Higgs boson searches, it's really trying to find the needle in the haystack. It becomes a classification problem. So we can use ML for this classification. How do we find a Higgs boson signal over a much more dominant collision background? Okay. So eventually, in 2012, at the LHC, when we'd gone to this higher energy, we saw a bump in the data, a statistically significant bump, and it's this bump which we can identify as the Higgs boson. So this got the Nobel Prize. That's a picture of Peter Higgs crying when he heard the news in the CERN auditorium. So that's the theorist that came up with the idea back in the 60s. The question now is, now we've discovered this particle, does it behave as we expect? So since 2012, we've collected...
That
Yeah.
picture was from 2012?
Yeah. Yeah. This guy, yeah. Still alive now. He's getting on a bit. You can tell he's getting on a bit there, and that was 12 years ago. So since 2012, we've collected around 20 times more data than we had at the time of discovery. So we've really turned our attention to precisely measuring the properties of the Higgs boson and how it interacts with other particles. So to do this, we basically need to find the Higgs bosons and then perform certain measurements of its properties. Okay? And then once we've measured the properties, we can compare to the predictions of the standard model, and deviations would allow us to say some things on some of the biggest questions we have in fundamental physics. So things like, what's the true origin of mass? Is the Higgs boson unique? Is it fundamental, etc.? And here's the Nature paper that I promised.
I'm looking for scale here.
Yeah.
How many particle collisions do you have per experiment? So,
as I said, we collide them 40 million times a second.
okay, yeah.
And these run like continuously. If you added all the time up, it's probably about a third of a year, maybe more.
Okay, so how often do you see Higgs bosons?
So it depends on how good our machine learning classifier works, right? So the better our machine learning classifier, the more we can identify Higgs bosons the better we can identify Higgs bosons from the rest of the background. To give a solid number, the decay channel that I work on most is this Higgs to 2 photon decay channel. From the data that we collected from 2016 to 2018 at the LHC, we have around 1,000 Higgs bosons of that data. Yeah.
Data.
Yeah.
So you said there's one for every 10
Billion proton, yeah.
Okay.
Yeah.
And that's the proton-proton collision happens 40 million times a second.
Yes. Yeah. But that does include the effect of something we call pileup, which is for each. When I say there's 40 million proton collisions, I actually mean 40 million bunches of protons collide per second. And in each bunch collision, you actually get many protons colliding, right?
Okay.
So that's something we call pileup. So you've got to factor that into it as well. But that's only like a factor of 10 or 100. Yeah. So
that produces more collisions. Or less? More.
That's more. Yeah. So each of these 40 million collisions, we have that's 40 million bunches of protons colliding per second. And then within these bunch collisions, you get, at the minute, we're operating around a pileup of 60. So 60 proton collisions. Yeah. So you can divide that 10 billion by a factor of 60. Yeah. So
It's probably like 15 orders of magnitude, the rarest thing.
Yeah.
Like 1 over 10 to 15.
10 to 15, yeah.
The probability what has been.
Probability of, yeah.
Not necessarily Higgs, but the rarest thing what has been.
Yeah. Unlikely. But because we collide enough, then we do get it in the data. Yeah. Okay, and then this is like another analysis. So I spoke a bit about the Higgs to 2 photon analysis. This is Higgs to BB bar pair. So a Higgs decaying to 2 bottom quarks. And the best channel to look for this is when it's produced in association with a Z boson, and your Z decays into an E plus E minus pair, for example. So the event looks like this. So your Higgs and Z decay instantaneously. You don't see them in the detector, but what you see are its decay products. So you get two so-called B jets, which correspond to the B quarks that are produced, and then you get these two towers of energy for the E plus and E minus. Okay? Now, if you think about in its very the smallest data compression we could do for that, if we only took the three components of each these particles' momenta, then that's 12-dimensional space. It's still high, right? There's 4 particles, yeah, or even in 4D it'd be 16. So it's really high dimensional space, which, as I go back to the simulation, it's hard to populate this space to be able to accurately estimate the density for inference. So we need to construct a summary statistic. Okay? So from this data, we construct a summary statistic, which, as you can see here, does a great job at identifying the Higgs boson signal in red from the background. So the background peaks towards the left, and the Higgs boson signal peaks towards the right. And then we can use these 1D histograms, these are our summary statistics, to fit the amount of Higgs boson production in the data.
So you have a histogram from a higher dimensional space and a histogram from the lower dimensions.
The higher dimensional data isn't histogrammed, right? This is just...
So you have a density in from the higher dimension and a histogram from the lower dimension.
Yes, yeah. It wouldn't need to be histogrammed, but it's the best way that we can accurately estimate the density, right? So we can use our Monte Carlo simulation of the background and the signal process to populate these bins. And then the black is what we measure in the data. The black points are what we measure in the data. And then we basically fit Monte Carlo simulation to the data to extract the underlying physics parameters, the theta.
So, kind of how similar two different density functions are is kind of what you're trying to...
How similar... Sorry, say that again.
So you have a density from a higher dimension, right?
Yeah.
And from a lower dimension, you have a histogram. So you kind of have a density through a histogram from a lower dimension. You're kind of trying to quantify how close they are.
It's not how close... It's basically what we want to do is construct a summary statistic which maximizes our information about the Higgs boson signal. So how can we define a summary statistic from our high dimensional data, so go from the high dimension to a lower dimension, where we can maximize the information about the Higgs boson.
And so maximizing information is having histograms that look different.
The better we can separate signal from background in this 1D, the better we're going to be able to measure the parameters of the Higgs boson. Okay? Yeah, so that's what the bottom's saying, right? Our inference task here is to measure, here I said the amount of Higgs boson production. So we have our density estimated in this histogram from the Monte Carlo simulation. We then scale up the signal by a certain amount until it fits the data, and that tells us how much Higgs boson signal there is in the data. Okay? And yeah, the quality of inference, so how sensitive we are to the rate of Higgs boson production, is tied to how well this summary statistic retains information about what we're trying to measure. So how well, in this case, it separates the background from the signal. Okay. So in the past, what we do for this construction of the summary statistic is to use some physically motivated variables for the dimensionality reduction. What we can do now is turn our attention to machine learning for this task, right? So we use a neural network parameterized by phi, which takes our input data of a high dimension D and puts this down to a lower dimension K. So in terms of a diagram, it would just, like a neural network architecture, you can just use an MLP that has D input nodes, which, for instance, would be the momenta, energy and momenta of these 4 particles that we measure. And then we want to boil that down into a lower dimensional space, okay, where we can tune K. In this example, we have a 1D summary statistic, so you'd have 1 node, yeah. Right, it depends how you define the the cross entropy loss. But yeah. Yeah.
How do you get your labels?
So to train it, we're training on the simulated data.
Okay.
So we simulate signal and background separately. So it intrinsically has this truth label. So we're just telling, we feed in our simulated data. We say, okay, this is a class background, this is signal, and then the output node will be like a probability of signal. And then we can use this to separate between the signal and background. Okay, so this is what we're doing, right? We have a neural network which takes from the high dimensional space to the lower dimensional space, and we want to find the network configuration phi, which maximizes the information about the parameters of interest, theta, in the output dimension, okay? And by doing that, we can increase our sensitivity to things like Higgs boson production and help answer some of these really fundamental questions that we have in physics. The method that I'm going to present to do this is inference-aware neural optimization, or IAO for short. But we'll come on to that after introducing a toy problem. So I think the best way to really describe this is to go away from the LHC and just picture the problem as a really simple toy problem. Okay? So in this case, we have a two-mixture model. Right? We have signal and background. And we want to maximize our sensitivity to the rate of signal production. The toy problem I've set up is with a known tractable probability density. So this is what we simulate our signal and background from. In reality, we don't have that luxury. Right? We needed that really complicated intractable chain to simulate our data. But for this toy example, I'm just doing a really simple known probability densities, where your input feature space is three-dimensional. So x0, x1, and x2, and they're distributed according to these functions here. So x0 and x1 are normally distributed. So Gaussians, for background, x0 has a mean of 2, so it's this orange curve here, and a width, a variance of 5. For signal, x0 has a mean of 0, and a much smaller variance of 1. Okay, so that's showing you what you see in this plot here. X1, for x1, the means of the two peaks overlap for signal and background, but the widths are significantly different. So for background, you have a variance of 9, whereas for signal, you have a variance of 1. And then the third dimension is this exponential decaying parameter. So x2, you can see from the plot on the right here, the rate of exponential decay is bigger for background. So we get a steeper curve. And for signal, it's more extended with a longer tail. Okay, so there are input feature dimensions in this toy example.
So they're kind of independent Gaussians.
Yes, yeah. Okay, sorry, I shouldn't really have written in this way. It's kind of confused it a little bit. The fact that these are 0 on the off diagonal means that they're independent Gaussians. Yeah. It's a good point. I think it was like the shortest notation that I could write. Yeah.
So is x0 and x1 independent with x2?
Yes, and x0 and x1 are independent as well. Yeah, because there's no off diagonal term here. Okay, so because we've got these known, let me say at this point, right? So we have these 3D input feature, and we're trying to construct a one-dimensional summary statistic. Yeah. So from these 3 input features, we want to construct a 1D summary statistic for our inference task of measuring the rate of signal production. And because we know the densities, then we can generate the synthetic data from these densities quite easily. So we generate a large sample of signal and background events. The standard approach for this would be to just train a neural network for this 2-hypothesis classification with a binary cross-entropy loss. I guess you've come across BCE losses before, right? So, yeah, that's what this histogram showing here, network architecture showing here. So you have your 3D input features. The way I have this network set up is actually with 2 nodes, but I have a softmax layer before them, so that these 2 nodes add up to 1. So they're not independent. So you can identify one node as the probability that the input event is signal, and the other node that the probability of the event is background. We can then take one of these nodes and histogram the network output, so say probability of signal, and we get what you see on the right here. So you see the signal events are peaking towards the right, so high probability that they're signal, and the background events are peaking towards the left, so low probability. Okay, all simple, right? And we can use the simulation to basically estimate the density of these bins in the histogram. Right, so then onto the statistical inference. So this follows what I was speaking about before. So let's assume that our total background yield is known to be 1,000, and our expected signal yield S is 50. So that's what you see by the histogram, right? So this is your neural network output. Now I've stacked the histograms on top of each other. So that's the total amount of counts that you'd expect to see in each bin, with a background of 1,000 and a signal of 50. And the black points are the data points that we observe at the LHC. Does anyone know how we'd then extract or infer the signal yield and its corresponding uncertainty from this problem? Maybe I can give a clue. So we want to write down the likelihood, right? And I think I've mentioned this before. The probability distribution that we're interested with these bins is the Poisson distribution. So it tells us the probability that we observe n events in data given some expectation in a given bin is equal to this formula here. Okay? We can use that then to construct a likelihood for the full histogram simply by just taking the product of the Poisson terms in each bin. Okay? So it's just the product of the Poisson for the observed data given what we expect from the signal and background simulation. All right? So that's what I've shown by these labels here. This is from the data, this is from the simulation. We then do the standard thing, take the log of the likelihood, well, the negative log of the likelihood becomes much easier because then it's just the sum over the histogram bins rather than the product. And you get this formula here. And then from that, we can construct a test statistic. So I don't know if you've heard about this, this terminology before, but it's the log likelihood ratio. This test statistic, well, -2 times the log likelihood ratio, where the numerator is your likelihood for a given value of S, and then the denominator is the likelihood at the best fit S. Okay, that's what I denote by this S hat notation. So we call that 2 delta NLL, and in its full form is this equation that you see at the bottom here. So we can use this test statistic to measure the rate of the signal production in data. Have you seen anything like that before? Or is that new stats?
So S hat is the best fit?
Yeah.
And S is what you're comparing?
S, yeah. So basically, this test statistic is a function of S.
Okay.
Yeah. So what we do, you'll see, actually, maybe should have put that up here, right? So we scan over possible signal values, yeah, and calculate this 2 delta NLL. And we get a curve that looks like this. Right? So your minimum of the curve, you can quite clearly see will happen when S is equal to S hat. So the point where the curve is 0 is your best fit point by construction. The other thing to say, then, what else can we learn from this curve? Actually, the point where it crosses a value of 1 is your 1 sigma confidence interval. So that's your plus or minus 68% uncertainty on your signal yield, right? So given this data, what this slide is showing is that we measure a value of 64 for the signal yield with an uncertainty of plus or minus 16, 17. Is that all clear from the figures? Because it's kind of important for what I'll show in the next few slides. So we have this test statistic that we plot as a function of S, and the point where the minimum is our best fit S, and where it crosses this 1 sigma, this value, this line of 1 is your plus or minus 1 sigma interval. So you're plus or minus 68% uncertainty.
And so this expected S of 50 is within the confidence interval, so we can not reject whatever.
Yeah, it's basically, exactly. We say, well, you can see it by eye, right? There's a slight excess, particularly in this bin where most of the signal lies. So that's why we've measured a value of above 50. But, as you say, the true value is still consistent with what we observe in data within 68%.
So in that case, basically you say...
You wouldn't be able to say anything statistically. So you wouldn't say, okay, we have an excess in the data. Yeah, you'd say that our data agrees with expectation. Yeah. All right. Have you heard of a concept known as the Asimov data sets before? No. All right, let me go through this then. This is a really useful and pretty simple method for extracting your expected sensitivity of a given analysis, right? I linked the paper here. The quote in the abstract is a simple method to obtain the median experimental sensitivity of a search or measurement as well as fluctuations about this expectation. Basically, what we do is just replace the observed data with what you'd expect to see under some model hypothesis, theta star. So our parameters, theta, take some value, theta star, and we replace our observed data with the data you'd expect to see under this hypothesis in the absence of statistical fluctuation. So it's as simple as just taking ni equal to si and bi at some value of theta. I've got a plot here which should show this explicitly. This is the case we had before, where you can see the observed data had some fluctuations around the expectations. Our Asimov data set on the right is the case where the data points line up exactly with what you'd expect from simulation for some values of theta, where theta in this case are our signal and background yield. Okay? What that's useful there for, then we can basically repeat the statistical test which I was describing on the few slides before, and you get a curve like this. And what's nice is that our best fit point, by construction, lines up with the expectation. Right? So by construction, theta best fit is equal to the theta that we've made the data set with. That's obvious. What it's useful for is the uncertainties. So these points here, where the curve crosses the 1 sigma, 2NL equal to 1 line, are your 1 sigma uncertainties. They're your expected uncertainties. Okay? So we can use that basically to evaluate the expected uncertainty, and then it's a great metric for comparing between different inference methods. So say for this neural network, we have a sensitivity here. We train something else. We get rid of the statistical fluctuations, and we can compare like for like by looking at the size of this confidence interval. So the more powerful the neural network is, the smaller the confidence interval on S. Right? The better we can measure this parameter. I've realised that I think that the like last part on normalising flows is probably not going to be covered. But anyway, it's around past now, so maybe we take a break, and then I'll go on to talk about the introduction of nuisance parameters. Okay. Does anyone have any questions about anything about the stats? Because I know it's kind of late in the day after a whole day of learning, but some of these ideas, they seem complicated. They're not too difficult, right? We've just wrote down a likelihood which was the product of the Poisson terms in these bins, and then we can use that likelihood to extract your best fit signal yield and your uncertainty on the signal yield.
So now if you go back to the next one, the next curve where you have the expected one.
Yes.
Under the S. So now if you find your best fit S on some simulation data,
Yeah.
and it's like outside of that confidence interval,
Yeah.
then you can reject.
Yeah, exactly. That's the kind of test that we do, right? So if we'd start off with doing this expectation, we show that our analysis has closure, what sensitivity we'd expect, and then when we're happy with the analysis, we unblind the data, we perform the same analysis on real data at the LHC, and say if we got a curve that like, went up like that and didn't align with this, then new physics. Yeah, we've found something that doesn't align with our model. And that's the whole idea, yeah. But what's great about the Asimov is it's this method to basically extract the expected sensitivity. So under some model hypothesis, theta star, what sensitivity do we give from this neural network that we've trained? And we'll use that as a metric on the inference-aware optimization, which I'll speak about after the break. Okay, where were we? Asimov dataset. Right, so we had a construction of an Asimov dataset which allows us to look at the expected sensitivity given our summary statistics. So we've trained a neural network, how sensitive is it to measuring the rate of the signal? Okay, so showing this slide again with a new title, the simulation is extremely complicated. Right, so the whole chain, we've gone from our mathematical theory all the way through to through the detector, how we reconstruct it, and we get our data. In this chain, there's a huge amount of unobserved latent features. So we ask ourselves, how do we know that our simulation perfectly models what we observe in the LHC data? Well, the answer is we don't. We can't do that, right? We can't say that our simulation is perfect. So that means for the inference, we must add nuisance parameters, which models these differences between real data and our simulated data. So they can be things like the particle energy measurement, particle identification, the number of collisions itself that we don't know exactly, or like the theoretical models of this hard scattering processes or the parton shower. So you can kind of like bifurcate your parameter list, theta, into two parts. One are your parameters of interest, mu, that you're trying to infer, and eta are your nuisance parameters. And then what we do is, well, as frequentists, we profile over the nuisance parameters. But if you wanted to do a Bayesian approach, then you'd marginalize over these theta parameters. But ultimately, this act of either profiling or marginalizing will weaken your constraint on the parameters that you're trying to measure. Okay? For this statistical test, we introduced the profiled likelihood ratio. So it's not so different from what I've shown before. I've extended theta into its two terms here. So in your denominator, you have your unconditional best fit point in mu and eta space. And in the numerator, so your test statistic is a function of your parameter of interest. And in your numerator, you have the likelihood evaluated at that value where your nuisance parameters have been minimized over to find the value which minimizes the likelihood for that particular value of mu. Okay? So we scan over eta space and find the eta values which minimize the likelihood for a given fixed mu. Now, this is kind of like the major part of all particle physics analysis, is understanding these differences between data and simulation and how we account for that by introducing nuisance parameters into our model. So an example here is the analysis that I work on. This is measuring the Higgs boson rate in the Higgs to gamma-gamma decay channel, so Higgs to 2-photon decay channel. You can see the kind of different systematic uncertainties, so the nuisance parameters that we have to introduce into the measurement. So it's things like on the photon identification, the energy measurements of our particles, right down to the theoretical model that we're fitting. Okay? So we introduce these nuisance parameters. I bring this plot up here. This is again showing a comparison of data to simulation. The pink band here is what we is a combination of the Monte Carlo statistics and your systematic. So we've basically introduced this systematic uncertainty to cover the differences between data and simulation. Okay, so we introduce these nuisance parameters to cover this difference. And then once we have this systematic uncertainty in our inference model, it's going to weaken our constraint that we can place on the parameter of interest, but that's what we want, right? There's some like lack of understanding of our simulation. It doesn't model the data perfectly, so we need to introduce this systematic uncertainty. So that's what you see here. This is the profiled likelihood ratio. So let's show the dashed first. So the dashed line is what we get without any nuisance parameters. And the solid black curve is what you get when you introduce nuisance parameters. And then from this profiled likelihood, you can see that this basically widens your likelihood curve. And this act of widening is increasing your uncertainty in this parameter of interest, right? So we've added nuisance parameters which have increased our uncertainty in our parameter of interest. And these nuisance parameters model our difference between observed data and simulated data. So our sensitivity is impacted by nuisance parameters. The question we can ask ourselves is how can we minimize this impact? I put these slides in just to give you an idea of where we're heading as a field in over the next few decades. So we're here now, you can tell I haven't updated this figure from the last set of slides that I put in. We're now at 2024. What the y-axis shows is, say, your uncertainty in some particular Higgs measurement, and the black curve is showing how this decreases over time as we collect more and more data throughout the operations of the LHC. Yeah, so right through to 2040. What you'll notice is that you kind of get this initial steep drop, but then it kind of flattens out, where increasing the data doesn't really help us much at all in reducing uncertainties. And the reason for this is that basically your total uncertainty consists of two components: your statistical uncertainty, which scales like 1 over the square root of the amount of data that you have. But then we also have this component from the systematic uncertainty, which we've been speaking about. And this doesn't have the nice scaling behavior. So eventually we reach a point where your systematic uncertainties dominate. They become the largest source of uncertainty in your measurement, and you don't really gain by taking more and more data. What I'll show is a method of introducing ML so that you can basically divert the field onto this other path. So how can we minimize the impact of systematic uncertainties in our measurements, which will lead to a fruitful exploration of the Higgs sector for the decades to come?
Ask, how did you get the nuisance parameter uncertainties? You had this ranking of them there.
Yeah. So that's done systematic. Well, you can do it. You can kind of do it systematically like this, right? So you see here, the dashed black curve is what we get when we remove all systematic uncertainties, and the solid black curve is what we get when we include all. You can one by one take away the sources of systematic uncertainty, and your curve will get smaller and smaller. And then we can take the difference in these curves to give you the impact from that particular source of systematic uncertainty, and that's how we rank them. So how much it affects your total uncertainty in the measurement. Okay, so then let's go back to our toy problem and add a nuisance parameter, right? So what I've introduced is this nuisance parameter R, which shifts the mean of your x0 distribution for background, right? So the function becomes this, where you have this nuisance parameter R, which shifts the mean. I've shown that in the histogram here. So the filled histogram is the nominal simulation, and then the x0 distribution when we vary R is shown by the unfilled histograms. Very simple as a nuisance parameter can get. And it's nice that in this case we can actually just have a simple differentiable transformation of our data. Right? So our simulated data, to go from a value of R equals 0 to R, we just simply add it to x0. Okay? So it's a really simple case. Now, what happens then if we look at the neural network output when we vary R in our data where we're evaluating the network on? Okay? So the blue and the pink is what we had before. These purple lines are what we get for the background when the background takes different R values. Right? So when it's produced with R equals 2, then we get this distribution here, and R equals -2 gives this distribution. So you can see that your probability density is changing as we vary the nuisance parameter R. And what's key is this bin here, where the signal accumulates. You can see that your background estimate in this bin varies quite significantly when we change the nuisance parameter, which is, of course, going to affect our inference when we're trying to measure the amount of signal. Okay? So we write down the likelihood. The difference now, so your likelihood is a function of S, B, and R. The difference is that in our background estimate, so our bin probability density, that becomes a function of R. That's exactly what I've shown here, right? Your background estimate varies as a function of R in each bit. Okay? So we use the Asimov data sets, where we throw the Asimov data set with these values of the parameters, so a signal of 50, a background of 1,000, and we initialize R at 0. So that's the data that we're fitting. And then we can look at this test statistic, 2 delta NLL, in the SR plane. Right? So for each value of SR in this plane, SNR in this plane, we can calculate the test statistic. And from that, we're able to identify the confidence intervals over these two parameters. Okay? So that's what you see here. The value, the interval where delta NLL is equal to 2.3 is your 68% confidence interval. So you know that that's basically your uncertainty, and then up to 5.99 is your 95% confidence interval. Now the thing to quickly identify from this plot is that the two parameters are quite highly correlated with each other, right? So by introducing R, we've introduced this correlation between R and S, which has basically increased your confidence interval on S. So we can no longer measure S with the same sensitivity. And that's shown directly here with this profiled likelihood curve. So think back to that curve that I showed where you're expanding, where you're introducing nuisance parameters. The dashed is what we had before, but if we do the profiled likelihood, so for each point as we scan over S, we minimize the likelihood with respect to R, and you get this solid curve here. Okay? And what you can see is that it's got much wider. So your uncertainty in your S measurement has increased significantly when we've introduced the effect of the nuisance parameter. And that's not what we want, right? We've lost our sensitivity to the signal. It's actually dropped by around 50% when we've introduced this parameter which can shift the background in X0. So yeah, conclusion. Our uncertainty on S has increased significantly, around 50% when we include the nuisance parameter for inference. And the reason for this is because our summary statistic, our network, this neural network trained with a BCE loss, has no information about R. Okay? It hasn't had any input from R, so it doesn't know how to deal with that. What we want to do is construct a summary statistic that does not diminish in power when accounting for the nuisance parameter. Is that an understandable task? Yeah. So we need to train our network in a certain way that it can basically overcome these changes in R, and we don't lose sensitivity to our signal estimate. And that's where inference-aware optimization comes in.
But
yeah.
Is there any information, like in practice, will you have any information about R?
Yeah, so what we can do, we know how R affects our data, so we can basically put this information into the training of the network, which will allow it to define a summary statistic, which basically reduces the effect of R on our measurement, which I'll show.
You know that in the toy data set.
Yes.
How do you know that in the...
Because we can simulate, so it's a good point. So like, we can do it by variational approximation. So here we have a nice differentiable mapping, like that tells us that, okay, we've introduced R, and we know that X0 goes to X0 plus R. That isn't always the case, as you say, but we can at least model how changing like one of these latent features will affect the data, will affect the Monte Carlo simulation. So let's make this detector have a slightly different calibration, and the energy measurement might increase by a certain amount. And then by doing this over the full simulated data, you can account for the effect of your nuisance parameter. Okay? So, yeah, the inference-aware optimization, the idea is basically for our network training, we redefine the loss function motivated by a specific inference task, where your loss is defined directly as an approximate of the variance in your parameter of interest. So I'll keep that there. I know that was a lot of words, like confusing words in a sentence, but hopefully it will become more and more clear when I go through the maths. And the result of that is that you basically construct a summary statistic which provides the smallest uncertainty in your parameters of interest. So we're going to feed information about the nuisance parameters in the network, and our result is a summary statistic which provides the smallest uncertainty for what we're trying to measure. That's inference-aware optimization. So we have a network. We take in the d-dimensional data For our toy problem, this was 3. We have a number of hidden layers, and then we have some output nodes, which we have m output nodes, right? So this is a tunable parameter in the training. And basically, as you feed the data through, for each one of these output nodes, you're going to get a score. So we can define straight away a naive summary statistic from this network, where basically we just take the argmax of these m nodes and put the data point in whichever bin is the argmax. Right? So say your network gives 0.8, 0.2, 0, 0, 0, then we put the event in that bin there, right? If instead this is the highest one, then we would put it in the third bin. Okay, so that's our naive definition of the summary statistic. And what you come on to see is that we can then do statistical inference on this naive summary statistic. Okay? So we do that by constructing the likelihood. This is exactly what I've shown before. So a product of Poisson terms in each bin of this summary statistic, where crucially your summary statistic depends on your network parameters phi. Right? So as you change phi, the weights and biases in these nodes, your summary statistic, your output values are going to change, so your distribution of the summary statistic changes. Okay. So we can define a likelihood. This is in terms of an observed data set. Of course, we can't do that. We need to construct an Asimov. So we get this equation here. So your Asimov likelihood at a particular parameter point is the product of the Poisson probabilities over these bins of the summary statistic. Yeah? Where your data takes the expectation for data is the Asimov data at some theta star. So once we've got that likelihood, we can do a Fisher information analysis to understand the uncertainty in our parameter of interest. Right? So have you come across Fisher information matrix, the Fisher information matrix before? It's basically, we can take our negative log likelihood at the best fit point, theta star, and expand in theta, where you take the second derivative, right? So this is basically a measure of the curvature of your likelihood function in parameter space. And the more curved your likelihood is, the more information you have about that kind of parameter, right? So that's what the Fisher information matrix tells us. Now, under Wilks' theorem, so this is the asymptotic approximation, the inverse of this Fisher information matrix is equal to the covariance matrix in our parameters of interest. Well, our model parameters. Sorry, I shouldn't have said parameters of interest there. That's all overall model parameters, right? So it's your covariance, in this case, over S, B, and R. And then we can define a loss function, which can be any function of this inverse Fisher information matrix. So, for example, the diagonal elements, kk, would correspond to the expected variance of parameter k. Does that make sense? So your inverse Fisher is your covariance matrix in the parameters. If we take your, along the diagonal of the covariance matrix, it's your variance in that particular parameter. And then we can define that directly as the loss. So your network loss function, as a function of your network parameters phi, is directly this term from the covariance matrix, i.e. we're trying to minimize the variance directly in the measurement, in the training.
This is a choice. Like you said, you can choose any function of the inverse, but
yeah. So
it seems like a natural choice.
This seems like a natural choice for one dimension, right? So we're in this case, in the toy problem, we're only trying to measure one parameter of interest, S. So in that case, it's clear we'd just take the 0, 0 element, which would be your variance in X, and that's what we're trying to minimize over. Now, in a case where we're trying to measure multiple parameters of interest, then it becomes a bit more of a choice. I'll go through that briefly in a few slides. But the idea now, we've got this loss function, which we can minimize with stochastic gradient descent. And as you do that, you're basically going to learn the summary statistic, which provides the smallest uncertainty in the parameter that you're trying to measure. So going back to the histogram and the network, as you're training this network, you're minimizing the loss. the definition of your test statistic is going to change to give you the summary statistic, which gives you the best sensitivity test. Okay? So that's the cool idea. I'll just go through like the technical implementation of this now. And firstly, just to say a few caveats with the idea. So the first caveat is that this is optimized for a particular value of the model parameters theta star. So you've evaluated this Fisher information matrix, the curvature of this likelihood at a particular point, right? So in principle, it could present problems. What the papers that have discussed this method have shown is that it's usually okay as long as your likelihood is like sufficiently parabolic and nicely behaved. If you have some weird non-parabolic likelihood where I vary significantly over your parameter space, then it may cause problems. Okay, so that's something to keep in mind when you're applying this particular.
So the convergence guarantees for this kind of loss function with SGD is well understood.
What's that? Sorry.
So like convergence guarantees for this kind of loss function where you're using is
Yeah.
with SGD is well understood.
By well understood, you mean like theoretically, or yeah? As far as I don't know if it is well understood theoretically, it works in practice. But it's a bit harder to tune than a BC, like a cross entropy loss. That's for sure. But you get better results. Caveat 2, right? So the Fisher information, this equation here, this second derivative, requires the derivative with respect to the model parameters. This comes back to our discussion before, yeah? So this can only be computed if your simulated data set is differentiable with respect to theta, or if you can model the effect of varying theta over the simulated data by a variational method. Right? So you have your simulated data, you see how does it change if I put the nuisance parameter up by this amount, and how does it change if I put it down by this amount, and then you can model this effect. So that's the variational method. But if you have a differentiable method, then it makes things a lot easier, because you can put it right in the definition of the loss. The third caveat is that the parameters of the network, phi, they're optimized with SGD. So your inference-aware loss must be differentiable with respect to phi. Now, did you spot anything as I was going through the method which is kind of wrong? Like what wasn't differentiable with the whole approach? Thinking about how we define the summary statistic in the first place.
How's the boson?
So before that, how we constructed T.
What's the sum of these things?
So what did we do? We took the
Argmax.
argmax. Yeah. And the argmax in itself isn't differentiable, right? So we can get around this by introducing a differentiable approximation of argmax, which is just softmax. Yeah? So your test summary statistic becomes this equation here. So for a given node I, where I runs from 0 to m, you just put it into this function, and this is like tuned with this temperature hyperparameter. So as tau approaches 0, as the temperature approaches 0, then your softmax becomes an argmax. But then there's a bit of a trade-off that as you go smaller and smaller, then your gradients become harder to deal with. So you need to find a sweet spot where you approximate the argmax well, but also have sensible gradients in the training.
But isn't finding the temperature itself like a problem? Like
So it's a hyperparameter that you'd have to do a grid search or optimization over. Yeah. But that's similar to any kind of training, right? Hyperparameter optimization. Just so this isn't the only way to make your summary statistic differentiable. I link a paper here which does a smoothing approach. Also, you could replace histogramming altogether and use some kind of like kernel density estimation. I'll not discuss that here. That could be left for further reading. So in terms of the technical implementation, the table and diagram that I show here, well, the algorithm and the diagram that I show here are from this Inferno paper. There's a slight change in notation from what I've presented. But hopefully you can see from the length, it's not super complicated, right? You have your differentiable simulator, which you simulate with some initial parameter values. And then you basically loop over epochs, you sample a mini-batch from the simulated data, and then from that mini-batch construct a differentiable summary statistic with this softmax function. You then construct the Asimov likelihood, and from that likelihood calculate your inverse Fisher information matrix, and then from that define the loss as the variance in your parameter of interest k. And then because you've made everything differentiable, you can take the gradient of this loss with respect to the network parameters and update them with stochastic gradient descent. So far, when I've been using this method, I've been able to do it all successfully with Torch's Autograd. And the tutorial, which we won't have time to go through, but I can provide the code for, if you guys are interested, uses Autograd. Of course, there's other products on the market, things like JAX, which are making a quick moves in the differentiable programming world, and so these are things that I could try in the future. All right, so then just to really spell it out for our toy problem, right? Theta is this list of S, B, and R. So what you do is mini-batch the simulated data, taking n signal and n background events, and then construct these test statistics with the softmax function, where the thing to notice is that your data for the background is varied, is a function of R. And this is that differentiable mapping that I showed. It's really simple, x0 goes to x0 plus R. Okay? And then from that, we construct your binned probability density distributions simply by just dividing the summary statistic by the number of events. We can plug this into your Asimov likelihood function and then take the Fisher information of this likelihood, so the second derivative at a particular parameter point. And then once we have that, we can define the loss function, which is directly the variance in your parameter, which, just to spell it out again, you're going to SGD over this loss, and over time you're going to develop this summary statistic so that you minimize the variance in the parameter that you're trying to measure. Okay. Does anyone have any questions? Yeah.
How about if the inverse is not behaving?
The inverse? How do you mean?
The matrix inverse. So it's like close to singular matrix. In a case, let's say some nuisance parameters will be sort of having the same impact.
Yeah.
But that might happen.
It might. I think what I'll go on to show is that, you don't need to do the full thing. You can make approximations. Right? So if you have a set of nuisance parameters, you could just use the most impactful nuisance parameters for this particular method, and then use that to minimize the effect of that.
Yeah.
I don't think you need to do everything, because then you could, as you say, once you include everything, then you could have some
because
tricky...
If they're collinear, basically super correlated.
Yeah. Then you could redefine what the nuisance parameter is by doing a rotation in parameter space. Yeah. Okay. So yeah, what was said here? Stochastic gradient, I think this is exactly what it said, right? Stochastic gradient descent of the loss will iteratively improve the summary statistic to maximize our sensitivity to the signal rate. That's the whole idea of inference-aware optimization. This is where I link the tutorial, so I can provide the slides later if you're interested. We're not going to have time to go through. I'll just present the results, right? So you had a question about the training or the convergence of this particular loss function. This is what the training looks like for our toy problem. So you see the train and test loss as a function of your number of epochs. And what's nice about this loss is actually you can define it so that on the y-axis it's directly your uncertainty or your approximated uncertainty on your parameter of interest. So as you're training, you're going from an uncertainty of 0.24 down to, 24 down to 17.
So you're converging to your systematic
free likelihood. Is that, yeah, basically, yeah. So what we had before was uncertainty of around 16, right? And you can see that, yeah, as we're learning, we're getting closer and closer to that. That's the idea, exactly. The hyperparameters, I just wanted to mention these. So one thing to say is that the batch size, so you mini batch the data. In this case, it actually needs to be large enough so that you can approximate your likelihood well. Right, so there's a part in the chain where you construct this likelihood function. If your bin probability densities are low in stats, then they're not going to be an accurate representation of the summary statistic. So in your mini batches, you need enough data to be able to accurately represent your densities. Then, as we spoke about temperature of the softmax function, you need this to be smallish to approximate the argmax, but also provide reasonable gradients in the training. Of course, learning rate is a standard. Another one then to say is the number of output nodes. So you can imagine, as you introduce more and more parameters, you might want to increase the bins in this histogram, right? So you can account for different shape effects from the different nuisance parameters. Then you're going back to the first hyperparameter. You kind of need to upscale your batch size so that you get sensible bin density estimates in as many output nodes as you want. Right? So those two are kind of like in balance. Okay, so then on to the results. The left is what I've already shown. So this was with the BCE loss and the confidence intervals in 2 dimensions, S versus R. And then on the right is what you get for the inference-aware loss. And you can see straight away that your correlation between S and R is reduced quite significantly. And in fact, the confidence interval for your inference-aware loss is much smaller than what you got for the BCE. Okay? Showing this explicitly with the profiled curves. So on the left is what we had before. You got this big deviation from the profiled curve and the fixed curve, meaning that our uncertainty in S was increasing a lot when we introduced the nuisance parameter. On the right is what we get for the inference-aware loss. So you can see that you've kind of like mitigated the effect of your nuisance parameter in the training here, and you have a much smaller drop in sensitivity when you include that in the inference. So that's the crucial idea. How, like I've shown a method that you can kind of tune the loss of your neural network to mitigate the effect of nuisance parameters in the inference. Okay. Right, let's see where we're at in terms of time. So then does anyone have any questions about the results? Is it clear what I've shown in the last 20 minutes? Yeah. All right, if not, then I'll go on and talk about like extending the inference-aware idea. So what we used before was just this likelihood here, Asimov likelihood definition. If some parameters new in your full parameter set theta are constrained by some like additional independent measurements, then we can basically supplement this likelihood with additional likelihoods by just taking the product. So we have our Asimov likelihood from the fit times these constraint terms from external measurements on these parameters. Let me try and give you an example. So in particle physics, we're trying to measure the energy of a particle as it moves through the detector. And depending on the scale, the calibration of our detector, we could measure the energy here, 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 or here, right? We could use other data to be able to constrain this scale down, this effect of the scale down. So we know that it can only go from here, here, and here. And then we can introduce this constraint on our energy scale by adding an extra term to the likelihood. And the way we do this typically is to add like a normally distributed term. So say you have some nuisance parameter nu, you could introduce like the observed value, which this basically penalizes nu as the nuisance parameter moves and adds something to the likelihood, right? Is that clear? You're basically adding a constraint term or adding information about the nuisance parameter into the network training. And this is where I want to try and just like stress the analogy with kind of like Bayesian inference. It's a way that you'd get like prior information about some of your other parameters into the network training by just like extending the likelihood. So that when you do inference-aware optimization, in the Bayesian sense, it's like taking the logarithm of your joint density, so your likelihood and your prior, and expanding around the MAP to a normal approximation of the posterior density. I don't really want to say anything other Bayesian, but this is a way that you could input prior information about your nuisance parameters into the training.
So you're kind of forcing your parameter nu to be close to.
Yeah, exactly. Yeah, you're penalising the nu away from nu. Multi-class, so this is, I think we've already spoke about this. What if our goal is to inference over several parameters of interest? So for the one parameter case, we just use the variance in that particular parameter. What if we're actually trying to infer multiple things? So as I said, the loss function can be any function of the inverse Fisher information matrix. For example, a very basic choice would be that your loss is just a composite loss, so it's the sum of the variances of your parameters of interest, where you can weight the terms in this sum, and these weights could be tuned by hand. So, you could run it once and say, actually, I want to know a little bit more about this parameter. Let's upweight that in the sum. The second is doing something a bit more like rigorous. So you get your covariance matrix from the inverse of the Fisher information matrix. You could then take the subdeterminant of the covariance matrix, which corresponds to the parameters of interest. So in this case, I'm just trying to show it pictorially. You could imagine your first three parameters are parameters of interest, and your fourth and fifth parameter are nuisance parameters. So what you do for the loss would just be to take the determinant of this this small subdeterminant, this matrix here, which just corresponds to the parameter of interest. Okay. One example would be, say, rather than just measuring the rate of signal, we want to measure the rate of two processes simultaneously. I'll show an example here, like measuring two different ways that the Higgs boson can be produced at the LHC. And initial studies show that the confidence intervals that we can get on these two parameters when using this subdeterminant of the covariance matrix is reduced substantially with the inference-aware loss compared to the cross-entropy loss, which is nice. And it's cool because you can actually kind of see this slight tilting this way. And that's because we've used the subdeterminant, we're really trying to penalise these off-diagonal terms which account for a correlation between the measured parameters of interest. Okay, so it was great introducing this toy problem because hopefully it's allowed me to explain the whole point of inference-aware optimization. It's clearly shown the benefit, but it is a toy problem at the end of the day. Our real-world analyses have much higher dimensional data, so we don't have three-dimensional simple data. We have many nuisance parameters, complicated likelihood functions, trying to measure multiple parameters of interest. I think what I wanted to say on the slide is basically just don't panic and simplify. So approximations of our statistical inference techniques can still do better than the canonical loss functions like cross-entropy loss. We can approximate, say, a complicated likelihood with these binned Poisson fits. And as I was saying to Mikhail's question, you could choose a subset of the most impactful nuisance parameters. So simplifying, you don't need to do the full statistical inference within your network. You can simplify the problem and still do better than a loss with a cross-entropy term. And yeah, this is really cutting edge. So it's not, as of yet, there's no publication that uses this inference-aware optimization with real LHC data. So I don't have any publications to show you, but these will come in the next year or so. All right, maybe this is something that could be a potential project for the poster or something to read about. After this is the mode collaboration. So what they're trying to do in this collaboration is the machine learning optimized design of experiments. So really use differentiable programming to globally optimize the design of detectors for particle physics analysis. Of course, when you come to design these detectors, you have a huge parameter space. So like your detector geometry, which technology you're using for the detector, which materials, how you do the data acquisition, information extraction, etc. The idea of mode is basically to make this whole pipeline differentiable. So, the whole point with this inference-aware optimization was to make the statistical inference differentiable. These really want to make the whole pipeline from the latent space parameters which define your detector geometry all the way through to your objective function, so your loss function, so that via stochastic gradient descent, you can find the detector configuration, which gives you the best sensitivity to what you're trying to measure. And I think where inference-aware optimization could fit in is into this objective function, which would allow us then to find like the detector configuration, so its geometry, technologies, materials, etc., which minimize the impact of systematic uncertainties on our measurement. An example is what they're trying to do with muon tomography. So this is where we have two detectors above and below an object, and as cosmic muons pass through, they leave a hit in the top panel and the bottom panel, and then from their hit patterns we can infer what happened in between these two detectors. So one potential use case for this technology is like scanning inside like cargo or trucks as they move through to see if there's any like dangerous objects. You could use the scattering pattern of muons to do this. And one particular like design of this detector will be where you put these detector materials in the X, Y, Z positions and how far these span. And if you can build this into a differential simulation, then as you simulate, you can find the configuration of these detectors, which will give you the best sensitivity to what's going on between the detectors. Application in other fields. So I think all of this has been quite particle physics heavy. I apologise. The problem is a very common problem, right? So many fields are dealing with intractable likelihoods with many latent features and use SBI to try and model this intractable likelihood. Many fields do deal with high dimensional data and require the construction of some lower dimensional summary statistic. Then we need to think, can you model how a change in your model parameters affect your data, either via some differentiable mapping or variational approximation? And if yes to these common questions, then inference-aware optimization may be able to improve your analysis. I put just an example with like 21 centimeter precision cosmology here at SKA. They typically have this kind of input data and need to boil this down to some summary statistics. The way they do this in the analyses is to use the power spectrum, and then from that they can infer these cosmological parameters. You might be able to use this technique to tune your summary statistic to maximize your sensitivity towards these parameters. Okay, I have this slide here, which is for further reading, in case you're interested. So starting with just like the frontiers of simulation-based inference, and then going on more specifically to this inference-aware idea. So section 5.4 of this second link here is a good overview of inference-aware summary statistics. And then the papers here show application to toy particle physics problems. As I've said, this is a new idea, so it's not been applied into any real LHC data yet, but just toy physics problems. And then I've linked related approaches in astrophysics and also this mode collaboration, which I spoke about before. Right, so to summarise, I think at that point, this will probably be the last slide that I show, and we don't have time to talk about the normalising flows, but that's fine. So SBI is a method that allows us to solve intractable likelihoods. Typically, the high-dimensional data necessitates this construction of summary statistics to allow us to perform SBI. And standard loss functions which we use for these tasks often prove inadequate when we introduce the latent features, so the nuisance parameters, basically. And inference-aware optimization is this idea where we can construct a powerful summary statistic. It maintains the inference power because we basically redefine the loss to approximate the variance in the parameter of interest and mitigate the effect of these nuisance parameters. And all of this has only been made possible due to the advances in differentiable programming over the last decade or so. So yeah, that's inference-aware optimization. Hopefully from the toy example you can see how that would extrapolate to a real-world analysis. But I think it's quite a cool idea. Do you have any questions?
About this the full optimization or a couple of slides ago then? probably works like if it's like differentiable near the sort of, just like fine tune the geometry. But it cannot like really sort of reinvent the whole experiment because that will require like global optimization.
Yes, agreed.
How do you see it? Because
No, I think that's completely fair. Yeah, it'd be like in this case moving the position of these.
exactly.
But it wouldn't be. Yeah, it's a lot harder to do a complete like a phase change.
Kind of like
Design.
science fiction kind of
Yeah.
reinventing the whole concept.
So my mate, when he did his PhD at the same time as me, did it about the magnet design for the ship experiment. And there they did try different like geometrical shapes. So I can try and find that paper for you. What's interesting as well, the objective function wasn't just like the sensitivity of your analysis, but also they whack in like how much it costs. Mm-hmm. So you get this composite loss of like how sensitive your particular detector geometry is with how much it would cost to build something. So you don't want to like have a really sensitive detector that's impossible to build. Yeah. Okay.
For the global pattern, you can use something else.
Like Bayesian optimization.
Yeah, right.
Yeah. Genetic model or something like that.